So what do we do today? I know. Let's finish up that problem set that we didn't quite finish. You recall that we were like 90% done with this chapter 5 problem set number 3. We saved for last the questions about geometric sequences as well as these last 3 word problems. So we'll do those now, and then we can dive back into chapter 6, where we basically just barely got started with it. So we'll pick it up there. So that pretty much will take up all of today. All right, let's take a look at this one. So first of all, you can see that this is very similar to the one we had before, except that we are now using geometric sequences. Now, you recall, of course, that a geometric sequence means that they have a common ratio rather than a common difference. So, for example, this one, it starts at 12 and has a common ratio of 2, which means that the first 5 terms look like this. All right, so that was pretty straightforward. So now what do we want to do? The next step is to find the 12th term. All right, so how do we do that? Well, there's a formula. All right, of course there's a formula. There's always a formula, isn't there? Yes. All right, so let's see what that is. The formula for figuring out the term in an arithmetic sequence is AN equals, oops, what happened? A1 times R to the n minus 1 power. All right, so whenever we need to find the specific term in a geometric sequence, this is the formula that we'll use. Now, like with the arithmetic sequence, we could write them all out, but they're going to get so big that it's probably better if we just fill in the formula. All right, and like this is no exception. It's a fairly big number that we're going to find here. So we're looking for the 12th term. And the first term is a 12. The common ratio is 2. And that exponent will be 12 minus 1. So you've actually got here 12 times 2 to the 11th power. And that happens to be 2048. Okay. 12 times 2048. And then when you multiply those out, you get 24,576. Now, we certainly could have done this ourselves by doubling each time, but I would say that the chances of making a mistake that way are quite high. Here, you just plug in the numbers and you're done. All right, and there's something to be said for that. Simplicity is always good, don't you think? Especially when it comes to math. Yes, complexity is not what we're hoping for, because complexity comes with the potential for making mistakes or else not understanding what you're doing. So simplicity is good. All right, you know what I mean. And in your own life too, don't you prefer simplicity to complexity? Especially in relationships with other people, simplicity is good. All right, everybody knows what's going on and you're fine. All right, now for the sum, the formula, let me enter this with the equation editor. And here we go. So Sn equals, so whoops, this one has a ratio. And that ratio is A1 times 1 minus R to the n power all over 1 minus R. So you don't need to figure out the nth term with this formula, but it is a bit messy. Okay, we may end up with enormous numbers when we do this, which is okay. It's not the end of the world. Okay, now let's plug in what we have. So since we're looking for S12, the n is 12. The first term is 12 again, and the common ratio is 2. This is raised to the 12th power. So you've got in your parentheses here, 1 minus 2 to the 12th is 4,096. All of that is divided by -1. Okay. So this one is now the same thing as 12 times negative 4095 all over negative 1. So the negatives drop out. And when you're done, you'll end up with 49,140. Man, that's a big number. Yeah, but wait till you see. We've got some real big ones coming up in the later problems. 49,140, that's a pretty big number, but not compared to what we're about to see with some of these other cases. All right, so 3 things are completely done. We've got the first 5 terms, which is straightforward. We've got the 12th term using that formula, and we have the sum of the first 12. Beautiful. All right. Now for the next question, we're essentially doing the same thing, except with slightly different numbers. So let's start out by writing out the terms. We'll have 8, 24, 72, 216, and 648, because each time you're simply multiplying the previous term by 3 to come up with the next term. No problems there. Okay, so for the sum, the 12th term, we'll use the same formula. So that means A12, which is what we want, is the first term is 8, R is 3, and we'll raise that to the 12 minus 1 power. Now, of course, that means what we're actually dealing with here is 8 times 3 to the 11th. 3 to the 11th. Ooh, 177,147. And when you multiply that by 8, you should get 1,417,176. Wow. It's probably just as well that we didn't try to do all this ourselves. We could have done it. I like, in this case, using the formula. Can you imagine what the sum is going to look like? Ooh, it's going to be a big one. All right, so what I'm going to do is I'm going to recycle this formula. This time, though, we have A1 is 8. So this is now an 8. The common ratio is 3. And that means I have to replace this one as well. So I'll have the ratio of, 8 times, now 3 to the 12th power, ooh, that is big, 531,441 over negative 2. So in parentheses, we now have negative 531,440 all over negative 2. So we're going to have 2 negatives that cancel each other out. We'll end up with a positive number, which is 2,125,760. Yeah, just as I thought, it's big. It's really big. All right, and so that one's done. All right, so far so good? Everyone's got them all right? Okay, you just have to be careful with them. They're not that painful. You just have to be a little careful. All right. Now, for these, we've got the actual numbers. And of course, we can easily identify the values of, let's say, A1. This case, it's 4. The common ratio is simply 3. How do you know? Because you have to triple each number to get to the next term. And once that's been said, look how easy it is to figure out the 12th term. Let's go back and grab this formula. All right, and let's see what happens here. We've got A12 is 4 times The common ratio is 3, and now that means the exponent will be 12 minus 1. Four times 3 to the 11th. 4 times, now we saw this earlier, 3 to the 11th is 177,147. And the final result is 708,588. Wow. So the numbers are getting big, really big. And then that leaves us to find the sum, which, our old friend here, which I will borrow this formula and recycle it, I guess. I don't know if that really counts as recycling. I'm using it again for a different purpose. How about that? So this time the first term is 4 and the common ratio is 3. So just have to make a few little changes in here. All right. So anyway, let's see what we've got. 4 times. So 3 to the 12th. It sounds like it's going to be enormous. 531. 531, 441 over -2. Wow. All right, let's see what this turns out to be. $1,062,880. Ooh, they're just getting bigger all the time, aren't they? All right, so those are your 3 results. Actually, here we only needed 2. We have the first 5 terms already, so all we need to do is find the 12th term and the sum of the first 12. Now the next one is very similar. A1 is 6, and the common ratio is 2 this time. So let's see what we've got. So the 12th term, A12, is 6 times 2 raised to the 12 minus 1 power. 6 times 2 to the 11th. 2 to the 11th. So that's 6 times 2048. And that multiplies out to 12,288. Yes. Okay, perfect. So now that all that we have to do is get the sum together here. And so, like I said, I'll just recycle this formula. So the first term is 6 this time instead of 4, and the ratio is 2 instead of 3. Okay, now I just figure out what those are. So I'll have 6 times 1 minus, now 2 to the 12th is 4096, all over -1. So I've got now 6 times -4095 all over -1. And that gives me 24,570. Okay, very good. Nice. Okay, now the next 3 are a little bit trickier, as you can see, because they involve fractions, and one of them actually has negatives. So we just have to be a little bit more careful with these. how would things be different? Well, first of all, if you look at this next one, you can see that the starting term is a half. What's the common ratio, though? How do we go from 1/2 to 1/4 to 1/8 to 1/16? Good question. Well, let's see what happens. How do I go from 1/2 to 1/4? Oh, yeah, look at that. And from 1/4 to 1/8? Oh my God, yes. So that means the ratio is also 1/2. That's the challenge. Once you got that straight, the rest is easy because A12, well, first AN, let's remind ourselves, is A1, R to the n minus 1 power. So that means that A12 would be 1/2 times 1/2. Ooh, interesting. So you know what this means? Because they both have the same base, there's an implicit 1 here. And so look what I can do. I can just write this as 1/2 to the 12th power. And then in turn, I can write that as 1 to the 12th over 2 to the 12th. And that's going to simplify to 1 over 4096. And you're done. All right. Now for the sum of the first 12 terms, so we have again 1 minus r to the n over 1 minus r. Now, because these numbers are fractions, the sum is likely to be fairly small, not like what we're used to seeing, like 2 million something. So S12 would be 1/2 times 1 minus 1/2 to the 12th all over 1 minus 1/2. Now, here's an interesting result. These cancel out. Well, that's convenient. Now, 1/12, sorry, this is not 12, this is 2. Yeah, that's 1/2 to the 12th. So this is basically 1 over 4096. All right, why? Because 2 to the 12th is in fact 4096. So therefore, now how do I consolidate these two expressions? They do not have a common denominator, so guess what we can do? We can make one. How? Oh my God, look how easy this is. And that's it. It adds up to a number which is just slightly less than 1. So as we predicted, the number is small because we're dealing with fractions. All right. So again, it was a little tricky, but not too bad. Now look at this disaster. No, it's not a disaster. Why? Because look at how easy this is. A1 is 2/3. What's the common ratio? Well, let's take a look. How do you go from 2/3 to 2/9? Oh, Look at that. It's 1/3. In other words, if you multiply each of these by 1/3, that will bring you to the next term. You can tell the numerator has to be 1 because these never change. This is what's changing. It's increasing by a factor of 3 every time. So once again, look how easy this is. Okay, so how would we do this? Well, what we can do is rewrite this as 2/3 times 1 to the 11th over 3 to the 11th. Now 1 to the 11th is just 1. So you've got, see, 3 to the 12th is going to be, now I think we saw this earlier, 3 to the 12th is 531, 441.
I have a question.
Go ahead.
So how did 3 to the 11th power become 3 to the 12th power?
Oh, watch this, because 3 times 3 to the 11th is the same as 3 to the 1st times 3 to the 11th. And then we apply our product rule. Because they have the same base, we can just add the exponents.
Gotcha. Okay.
That's how these became this. Don't forget, there's always that implied 1 there. And because they have the same base, we can simply add their exponents. Not here, of course. These are 2 different things, but 3 to the 1st times 3 to the 11th is 3 to the 12th.
Gotcha. Okay. Thank you.
You're welcome. All right. Now that was A12. Now what about the sum? Ooh, no, it's not going to be that bad, because look, all you have to do is this. So we started out, oops, this is A1, not A, it's A1. A1, remember, was 2/3. One minus the common ratio we determined, remember, was 1/3. So we'll have 1/3 to the 12th all over 1 minus 1/3. Now look what happens this time. 2/3, 1 minus 1/3 to the 12th. I should put this in parentheses to remind you the whole expression is being raised to the 12th power, not just the 1. And look what I end up with in the denominator. So we can rewrite this as 1 minus 1/12 over 3 to the 12th. But 1/12, I mean, 1 to the 12th is just 1. Okay, we've already seen that this is 531,441. And now look what we can do. Ooh, how easy is this? Okay. Look at that. Now that's really, really close to 1, isn't it? It's not quite there, but it's really, really close. Now we saved the best for last. We've got one with negatives. And we haven't seen that just yet in this problem set. Negatives. Is that going to be a problem? Not really, because it just means that the ratio is negative. Okay, so we start here with A1 equals 3, -3. Well, actually, no, sorry, not this time. R is just +5. I'll tell you why. Because in order to go from here to here, multiplied by negative, oh, no, I had it the first time, sorry, -5. And then from here to here is -5. Yes, that's right. So it's -3 and -5. So then our formula will be -3 times -5, okay, or -3, -5 to the 11th. Man, we're looking at a big, big number, aren't we? -5 to the 11th. Wow. Ooh, this is a big one. Ouch. -48,000. 48,828,125. Now, of course, you've got, sorry, this is negative. So these are both negatives. So we'll end up with a positive number, which is 146,484,375. Man, that's a big number. And we're not done yet because we still have to do the sum. Oh, it boggles the mind to think how big that number is going to be. Yep, that's going to be a whopper. So S12 is, we start out with -3, 1 minus -5 to the 12th, all divided by 1 minus -5. Wow, that's a scary looking formula. Oops, hold on one second. That's better. All right, so let's plug everything in here. You've got -3. Now, -5 to the 12th, because that's an even exponent, is going to be a positive number. 244 million 140 625 over 6. So this is actually -244. Man. And that's going to equal 122 million 70. No, wait a minute. Yes. Hold on. 244 million 140,000 624. That's negative. Times -3 divided by +6. Oh, there's two negatives there. That's right. Yes, it's 122,070,312 exactly. Oh boy, those were brutal. But they're done at long last. They're done. Okay. Jeez, that was a hard one. Now, the next three are word problems. Now, these word problems, I'll tell you in advance, they're all based on what we're doing here. They're either arithmetic or geometric sequences. It's just a question of recognizing what you're supposed to do with them. All right. So when we're ready, we can move on. Now, if you have a car, you understand this next problem very, very well. What happens to the value of your car every year? It goes down. That's right, down. Only one direction, down. Okay, that's exactly right. And the process is that by which this is happening is called depreciation. Like if you buy a new car, it's worth a lot of money. By the next year, you put 15,000 miles on it and it's not worth as much because it's no longer brand new. Oh no, not even a license. What state do you live in? And then why? Oh, I'll tell you what. There's some areas of the country where not having a car is not a problem. Like if you live right smack in the middle of Manhattan, you'll never need a car. Probably not. Certain cities, it's easy to get around by foot or by subway. Um, see, somebody else has a permit. Certain areas, well, you're not going anywhere without that car. Um, Trains are nice if you're close enough to them. Okay. Um, so I don't think we should get too further into this, but why not? What are you waiting for? I know. All right. When you get around to it, when all this nonsense is over, then you can go ahead and get one. The only problem is you have to have a car to practice with. Is that a problem? Actually, you can get a permit without. I think all you have to do is pass a test of some kind to get a permit. The permit gives you the right to learn how to drive and be on the road, but somebody else has to be with you. Well, I'll tell you what, don't put it off too long. Right, that's all I can say to you. Don't wait too long. Otherwise, the places you can work will be very, very restricted. Um, I mean, Manhattan would be nice, but the rents are out of control. So, we'll see how that goes. My niece lives in San Francisco, and she never got one. She just decided it was too scary, and so she just doesn't have one. Um, and she's not going to get one either. But she doesn't really need one in San Francisco. But you know what? It's just okay. But no, but one time, I mean, it's one of those things where even if you never drive, you really should have a license in your pocket just in case you need it. You never know when it might happen. But you know what? That's up to you. But of course, right now, it's probably not going to be possible to take a test. But when all this crap is over, maybe you should think about it. All right. Anyway, so having said that, though, even in spite of that, you do know that the car loses value every year. But the rate at which it depreciates does tend to shrink over time. In other words, the difference between a new car and let's say a 2-year-old car is quite a bit more than let's say the difference between a 6-year-old and an 8-year-old car. As the car gets older, the depreciation shrinks. Initially is when most of the depreciation takes place. So here we're looking at a situation where we're going to assume that the depreciation looks like this. So I'm going to treat these as negative numbers because they represent a loss of value. And we're being told that this is what the depreciation looks like for the first 3 years. Now, do those 3 numbers remind you of something? Just take a look at them. Is there a pattern there that you suddenly notice? What kind of pattern are we looking at here?
500 is being taken away.
Right. So we start with negative. Now, because these are negative numbers, oh, here we go. And somebody else has an answer. Yes, 500, exactly. So we start with negative 3,500. Now, because they're becoming less negative, the common difference is actually positive 500. Okay. So now it says here, how much value does the car lose in the 7th year? So they're basically asking you for the value of A7. All right, so if you recall from earlier, we had this formula for arithmetic sequences. A1 plus n minus 1d. So A7 in this case is negative 3,500 plus 7 minus 1 times 500 . Okay, so there's in year 7, the total depreciation for that year will only be $500. Okay, by that time, the car's value is pretty much stabilizing. The amount that it goes down after that will be very, very minimal. Okay. Now, part B is the tricky one. How much is the car worth at the end of the 7th year? So basically, what you're trying to figure out is how much did we lose through depreciation, and then add that to the car price. Okay, so in other words, what we're going to do is first figure out the sum of the first 7 terms, S7. And remember, for these cases with arithmetic sequences, the formula for Sn is okay, we'll get that equation editor going because it's a ratio, Sn so here we're going to have n times A1 plus An over 2. All right, so that's our formula. But we're specifically interested in S7. So let's figure this one out. S7. Now, N, remember, we're looking for the 7th year. We start at negative 3,500. And the last year is negative 500, as we've already determined. So you're adding a negative number here, basically. I'll put it like this. And so what you've got in your numerator is 7 times negative 4,000 all over 2 equals minus 14,000. Now that means we've lost $14,000 in value. Therefore, the value of the car must be 27,000 minus 14,000, 13,000. All right, that's how much it's still worth because of all that depreciation. All right, does that make sense to everyone? All right. All right, now, why don't we try this next one? Now, this one's interesting. There's a certain unnamed university here where parking tickets increase in value each time you get another one. So let's say you decide you're in a hurry, you park in the faculty lot and you get a ticket. The first time, the ticket is worth $5. The second time, it's worth $8. The third time, it's $11. Oh, there's a pattern there. So what does this remind you of? What kind of a sequence is this?
Arithmetic?
Yes, you have it right, exactly. Where A1 is 5, and the common difference is 3, and it keeps going up and up and up. So you don't want, they're trying to discourage you from doing this, okay? No tickets, please. But if you do, you're going to pay more and more for each one. So now here's the problem. We have this student who's convinced her parents to pay all these fines. She apparently does this all the time. So they've said to her, listen, yeah, we'll pay them, all right, but if your fines go over $100, we're going to sell your car. And you're going to walk to school from now on. The unfortunate thing is that she's already got 8 tickets. So what's going to happen to her? Well, what we need to do here is solve for Sn, but in this case, n is 8. What is the sum then of the first 8 tickets? Now, if you use this formula for the arithmetic sequence, you'll notice that we're missing an important piece of information. We need to know the value of A8 in order to do this properly. So we'll go back to our formula and we'll see what AN is. So we started with 5. We've got 8 tickets. The difference is 3. Oh boy, that last ticket is $26. Ooh, this isn't looking good, is it? So let's plug our numbers into here. Oh boy, I think somebody's going to be getting a lot of exercise this semester. So we've got S8 is 8, and then we have 5, and the last ticket was 26. Ouch. I don't think they really work it like that. They probably, it's just the same every time, but after a while, they, let's just say they will not be happy with you. And that, sadly enough, is $124, which means no more car. Oh, well. But you know what? 8, that's a lot of tickets. Come on. All right. Now, this last one, I've decided that it's too complicated to have on the next test, but I want you to see how it works anyway. All right. There's different ways we could go about this problem like all of the others. This is a geometric sequence problem because look what happens. You start out with $500 in your savings account, and at the end of the year, you'll earn 5% worth of interest. So the way we want to look at this is as follows. At the end of the first year, the balance will be 500. Then you're going to multiply by 1 plus that rate of interest. And that means that when the year is over, you'll have $525 in your account. The second year, the balance will be 525 times 1.05, which is 551.25. And then we'll do one more at the end of the third year. The balance will be 551.25 times 1.05, which is 578.8125. So this is a geometric sequence where A1 can be thought of as 525 and R is 1.05. Now, when they say how much money will be in your savings account at the end of the 10th year, what you're really being asked to solve for is A10, not S10, but A10. Because each term represents the current balance in your account. Okay, so if you recall from earlier, AN equals A1 R to the n minus 1 power. Okay, and so that's going to be, 525 times 1.05 to the 9th power, and that works out to be, let's see, 814. It's a very long number, so we don't need all those digits. Let me just show you what it looks like. It's, 814. There's a lot of decimals, 4, 4, 7, 3. So in a banking situation, this would be rounded to 814.45. Okay, because they only can pay you in dollars and cents. They can't give you fractional cents, can they? No, they cannot. Unless you've seen a 1/10 of a cent coin floating around, have you? No, you have not, because it doesn't exist. It only goes down to 1 penny. Which, by the way, has anyone here been to Canada in the last 5 years or so? They did something that I never thought any country would ever do. What did you notice when you spent money in Canada that is not true in the United States? Okay, now I hope you were paying attention when you were, every time you bought something, you might have noticed something strange going on. Oh, you weren't paying attention. What happened is that they got rid of the penny. So every time you buy something, the price has to be rounded up either to the next nickel or the next lower nickel. So if you bought something for $12.31, they would round it down to $12.30. But if it was $12.33, they would round it up to $12.35. Now I couldn't believe it when I noticed it just by accident. I was looking at my change and I said, I think you made a mistake here. I said, no, that's how we do it now. And like, what the heck, So apparently they decided that it wasn't worth their while to mint pennies anymore. And now everybody has to round everything. And I asked a bunch of people and none of them seemed to mind. But I don't think they would ever get away with that here. It's the same thing with the $1 bill. The $1 bills, they wear out very quickly. And, the federal government has to replace them. And so in a lot of countries, their $1 bill became a $1 coin. Or in the case of England, the £1 note became a £1 coin. In the US, they're constantly trying to pull this off on us. They're trying to say, listen, we're making all these $1 coins because you use them, for God's sake, so we can get rid of the $1 bills. And Americans say, nope, sorry, we're going to keep our pennies, we're going to keep our dollar bills. And that's the way it is. But in Canada, they just said, oh, what the heck, let's get rid of them. And we'll just have nickels. And so sometimes you win, sometimes you lose. I guess they figure over your lifetime, oh, we still have $2 bills. It's just that nobody uses them. Yeah, they're still out there. They're perfectly valid. I don't think they mint them anymore because there's already enough in circulation. But people, when they see them, they take them out of their change, their wallet, and they stick them in the drawer, and that's the end of them. It's like 50-cent coins. Half a dollar, John Kennedy is on the $50. And supposedly the government has minted enough 50-cent coins so that every single person in America could have 300 of them. And yet, where are they? They're piling up in people's drawers. They save them because they think they must be very valuable. They're not, but people think they are, so therefore you don't see them anymore. But they do exist. In fact, I bet there's many of you in the room who in your entire lifetime have never even seen a Kennedy $50. This is what it looks like, in case you were wondering. Look at that. Have you ever gotten one of these in your change? Have you ever seen one?
Yes.
You
Many
have.
have.
All right. Well, then you're
Not
very.
in circulation though.
Oh, where did you see it?
I collect coins, so
Oh,
yeah.
all right. So you have some. You know what I'm talking about.
Yeah, I have a whole roll of them.
Okay, but a lot of people who
But
don't.
never in circulation.
Right, exactly. But I mean, they're out there and people just hoard them, and that's the end of it. And you never see them again. They've been minting these since 1964, and yet where are they? They're in people's drawers. That's where they are. Okay. So yes, there it is. And there's actually, I think they're still making dollar coins, although I don't remember. They keep changing their mind with that one. But yes, these are perfectly valid. And yes, see, now the early ones, 64, I think, was the last year we had silver coins. So if you get one with silver in it, it's worth a lot more than the following ones, which were made out of this sort of hybrid material, which is copper, nickel, and zinc, I believe. So the silver coins are obviously worth a lot more. But yeah, they still have $2 bills. Does anyone happen to know whose picture is on it? Well, I guess somebody does. There we
The
go.
signing of the Declaration of Independence.
That's right. And so who's that guy in the front? Who is this guy?
Jefferson.
That's right. Exactly. It's still a perfectly valid, perfectly legal tender, but you do not see them very often. But in a lot of these countries that have $1 coins, they also have $2 coins. Canada has a $2 coin, and you see them all the time. You probably notice that when you're in Canada, you're constantly getting them in your change. In fact, the naming convention is pretty interesting. The $1 coin has a picture of a bird on the back called a loon. So they call it a loonie. And then the $2 coin, because of that, is called a toonie. That's how it's done up there. All right. So if somebody says, "Do you have a toonie in your pocket?" they mean a $2 coin. Okay. They're not losing their marbles. They mean it's a $2 coin. And you see them all the time. That's right. They have loonies and they have toonies. They don't have, so the paper money doesn't start until $5. All right. In England, it's the same thing, except it's £5, which is worth about $7 US. So the US is sticking with the $1 bills and the 1 penny. And we're going to stick with it. And the government can't say anything otherwise because they need our permission to make these changes. That's right. So we're going to stick with what we have, whether they like it or not. And besides, come on, how much money do you think the Canadian government is really saving by not minting pennies compared to the amount of money they spend every year? It's not that much. But they made the decision, and I'm sure they must have put it up to a vote. I don't think they would have just arbitrarily stopped making pennies because it affects everybody, but that's what happened. So it's like, well, you just have to get used to it. And I said to them, these people in the store, I mean, isn't this a pain to keep constantly having to do this? And they said, nah, you get used to it after a while. Well, I suppose that's true, but that doesn't mean you want to do it. All right. Well, anyway, so this one is done. Now this problem set is completely done. So now we can go back to chapter 6. Yay. Okay. So I'll post this when we're done and you'll be able to look at it to your heart's content. Now, I do want to point out, though, not that this is imminent, but the first midterm is based on chapters 5 and 6. So when we're done with 6, and we're done with all the problem sets, we're going to have what I call a sample midterm, which consolidates all of this material into one big practice problem set. And when that's done, then I can actually give you the first midterm. But don't worry, you'll have plenty of advance notice. You'll have plenty of time to do it. There's no rush. But it's coming eventually, maybe a couple of weeks, 3 weeks from now, but it's getting closer. Just because, like I said, it's based on 5 and 6. Now, here in chapter 6, we just barely started. We were looking at simplifying and evaluating expressions, and then I think we stopped with this example, which is Starbucks. Now everybody knows and loves Starbucks. So let's assume you walked into the Starbucks and the lattes cost $2.89 and the sales tax where you live is 6%. What is the total cost of the latte? Now, normally they do this for you. You just say it's, X dollars and you pay it. How would you figure out the total cost then? What would be your approach? What do you think would be a good strategy for figuring this out? Let's say that the cash registers, for whatever reason, the computers at Starbucks, the part that calculates the sales tax is not working today. So they have to do it all by hand. So the person behind the cash register has a pen and a piece of paper. And they say, all right, you're getting a latte for $2.89. Sales tax is 6%. How much should I charge you? What approach would they take? Anyone have any ideas? There's a couple of ways we could do this. By the way, I forgot. I couldn't tell who was it that told me that they're collecting coins?
Oh, that was me.
Noah? Okay,
Yeah.
I wasn't sure for a second. All right, I just want to ask you this trivia question then. You probably know the answer to this. What is the smallest denomination coin the U.S. government has ever minted?
I believe it was a half a cent.
You got it. All right, that's what reminded me before.
They also made 3-cent coins and they made 25-cent bills. There's a lot of like unusual types of currency that people don't know about.
Absolutely correct. Yes, they've had some very oddball coins, 3 cents and paper money.
I believe there might have been a 4-cent one, but I'm not sure about that.
I've never actually seen one of those. The reason why
Maybe
they
it was
had
4 cents or 6 cents that I'm thinking of, but it was one that I just discovered recently existed. So it was made for a very short period of time.
that's right. And the reason why that happened is because they didn't have enough silver.
It wasn't
and gold.
necessary, really.
Yeah, but
Like they realized it was easier just to have people use multiple coins for the result.
yeah, but the problem was that they were running out of coins. This is during the Civil War mainly, and
Yeah, the 3-cent coin was called the Trime. TRIME, kind of like a dime except with a T, with TR.
it was originally made out of silver, but then eventually they switched to nickel because
Yeah,
people were losing.
Nickel was invented well, it was first created right after the Civil War. It was in 1867, I believe.
That's correct. Yeah, man, you know your stuff. All right. Well, anyway, let's get back to this stuff. Maybe next time we can do this some more, but hold on a second. Yes. Noah the numismatist. That's right. That's what it's called. Numismatist is one who collects coins. And that is a very addictive area of collecting, isn't it? Once you get started, you can't help yourself anymore. That's
That's
right.
not my main collection. I mainly collect antique bottles.
Oh, no, but the coins are pretty cool, aren't they?
Yeah, I collect coins too. Yeah, it's one of my most important collections. I have a few, but my main is bottles.
The bottles take up a lot of space, though, don't they?
Yeah, it fills up my whole room.
I bet. The coins are nice.
Yeah, sorry for getting you off topic. I guess we'll get back to class now. Sorry.
That's all right. No, it's fun. No. There's plenty of room for having fun once in a while. I mean, come on. This is, it's not supposed to be deadly serious 100% of the time. I mean, come on. There's always room. You can think of these as applications of what we're doing. It's fine. No, I don't know anything about bottles either, but all right. Anyway, so here's one way you can figure out what you would pay for your Starbucks latte, and it's not the only way. So what you can do is you can break it up into two components. The sales tax would be 6% of 289 or 0.06. Now you can consolidate these algebraically because there's an implicit one here. Okay, in other words, 289 is the same as 289 times 1. So that means if you've got an expression like this, you can consolidate this into 2.89 times 1.06. And that's what you've actually done here. And then even though you have to round it, and again, there's this discussion about fractional sense. If you actually multiply that out, it is 3.0634, but of course we don't have fractional coins, so it would just be rounded to 306. And of course in Canada, it would be 305, as we now know. And that's how it's done. Okay, so now anytime you go into the Starbucks, you can take out your calculator and say, yes, they did this correctly. You can confirm it without just taking their word for it. Now, what's interesting is has anyone here ever been to a Western European country? All right. Well, the only reason I brought that up is because if you go to a Western European country, like let's say England, what they tend to do is rather than having a price followed by a sales tax, they'll tell you what the price is, including the sales tax. So let's say they tell you, you go into a Starbucks in London and they say the latte is £3. That means £3, including the tax. You just hand them £3. And, you know, I mean, if you like round numbers, you might say, oh, yes, go ahead.
I just wanted to quickly mention, I looked it up. I was talking about a 20-cent coin is what I was thinking of.
Oh, 20. Okay. That must
That
have
was
been
made for a very short time.
Yeah, because they stuck, you know, this is if you notice, most countries don't have a quarter. The US and Canada are two of the few countries that actually have a quarter. Most countries have a 20-cent coin instead of a quarter. Yeah, okay, so that's actually very interesting. But anyway, now what we're going to do is look at the opposite case where instead of a tax, we're going to look at a discount. Imagine yourself, you're in your room with all these roommates and you've got a couch, but it's all beat up and you know that you need a new one. So you look in the internet and you realize that Macy's is having a big sale on couches. And they're just right down there in White Plains. And you say to yourselves, let's go check this out. So they tell you in the ad that the couch normally costs $600, but if you come in now, we'll give you a 20% discount. So how would you figure out the actual price of this couch? Ooh, let's think about that. Well, we can do something similar to what we did with Starbucks, except that instead of positive 6%, we could think of it as negative 20%. It's almost like a negative tax. And so, again, with the understanding that there's an implicit 1 here, 600 could be thought of as 600 times 1. So if I have 600 times 1 minus 600 times 0.20, what I've actually got here is 600 times 1 minus 0.20, which in turn is 600 times 0.8. And that, as you can see, works out exactly to $480. And of course, there would be sales tax, but I mean, the retail price would be $480. And you'd all say, woohoo, we saved all this money. Let's get that new couch. Okay. And yeah, a lot of times these stores tend to put furniture on sale in the spring. I don't remember exactly why, but that's a common practice. Okay, now we're going to move into a new topic called solving linear equations. Now, when you look at that word linear, what word do you notice hiding in there? Line. So what we're looking at is equations of a straight line, which you recall, which nobody ever forgets, y equals mx plus b. M is, of course, the slope. B is the intercept. And so what we're trying to do here, though, is look for a specific point, the point where it crosses the horizontal axis. So let's say we have this. Oh, let's not try that one. Let's try a different one. Actually, let me put it on another slide. This is too small. So here's my linear function. It's clearly a straight line with a slope of 2. And the intercept is 4. All right, I'm out of space. I'll just put int. Intercept equals 4, which means right here is the point 4, 0, meaning that x is 4 and y is 0. I'm sorry, no, I wrote it backwards. I'm sorry. Yes, I did. It's 0, 4. It's the opposite of what I just said. 0, 4. The x is the one that's 0. The y is 4. But what we're interested in now is not the vertical intercept, but what is sometimes called the horizontal intercept. Where does this function cross the x-axis? Now, how are we supposed to figure that out? Well, the key detail here is that when we're at this point, y is equal to 0. What we need to figure out is the corresponding value of x. So how do we do that? Oh, I have an idea. Why don't we just set y equal to 0, and we should have our answer, okay? So again, y equals 2x plus 4. If I set that equal to 0, I can solve by subtracting 4 from both sides. And now I can divide both sides by 2. So therefore, minus 2 equals x. So here, x is minus 2, and y is 0. So this point is actually negative 2 comma 0. But this is what I'm interested in right here, the value of x at which y is 0, and this is referred to as the solution of this equation. All right, so it's the solution, and that just simply means what value of x causes the function to have a value of y, 0. Now, most of these cases, we're just doing simple algebra, all right, but sometimes it can get a little messy, but because this is a straight line, the equation can't get extremely messy. There's a limit to how messy it can get, because we're never going to have any x squares or any, anything like that. All right, now this is the kind of thing I'm sure you've done before, but you might be able to use a little practice with it. So here's our first very simple example. All right, are we ready? How about this one? What would you do to solve for x in this case? Well, our basic strategy is to do this. Isolate x on one side, either side is okay, of the equation, and the constants on the other side. That's what we're basically doing. And then you'll be done. We want just x, not some function of x, but x itself should be on one side, and the constants all move over to the other side. And when you're done, you'll have your answer. So like here, the first step we'll follow is to get the 7 over here with the 15. Now, how do you do that? Since this is a positive number, of course, that means we have to subtract. So let's see how that looks. That gives us 5x equals 8. And now what do? We don't need to know the value of 5x. We want x. So now the next thing we would do is simply divide out that 5 from both sides. And what do you know? We have our answer. And we can double check. Let's do that over here. Just go back to the original equation and plug in x for 8/5 for x. So this 5 times 8/5 is 8. Oh yeah, that means we must have done it correctly. Very good. And that means we've done it correctly. So, all right, so you can see, you get the idea. It's not that difficult. And so what do we do next? Let's try another example. All right, here we go. Ooh, all right. Well, here the answer is right in front of you. So unfortunately, that spoils the surprise, doesn't it? Yeah, but that's okay. What's happening here? Let's subtract the 9 from both sides. And that means we have just 33 on the right-hand side. To get rid of this -3, we just divide both sides by -3. And so you end up with -11. And we can prove it again by very simply replacing that x with -11 and seeing if it works. Oops, this is equals, sorry. And that proves that this is correct. All right, now the next one is a little bit trickier. So just because I think we could use some practice, rather than me showing you the answer, I'm going to show you the question, and then I want you to figure out the answer. All right, are we ready? So imagine you were confronted with this one. Oh no, look what a mess this one is. All right, so just for a fun little challenge, why don't you work on this for a couple of minutes and let me know what you come up with for X. It'll be more fun than if I just tell you the answer. All right. Let's see. Now the first, oh, we got plenty of answers. Ooh, I'm impressed. -3 it is. Okay, if you have 7, then we made a slight mistake. We'll fix that right now. Here's what you had to do. First, you want to multiply these terms by the 3. 3x minus 6 plus 4 equals 2x minus 5. Now, since these are already together on one side, let's consolidate those before we do anything else. And let's just decide that we'll put all the constants on the right-hand side. So we need to add 2 to both sides now. And that leaves us with, so I'm adding 2. Actually, let me show it explicitly here. And of course, by doing this, I'm not changing anything. I'm doing the same thing to both sides of the equation. Now I'm going to subtract 2x from both sides. And that is actually correct. And if you're not sure, once again, we can easily double check that. Why don't we do that right now, as a matter of fact? All right, so we start out with 3 times x minus 2 plus 4 equals 2x minus 5. So we're replacing the x's with -3. Three times -5 plus 4 equals -6 minus 5. Minus 15 plus 4 equals -11. And oh yeah, what do you know? In the next step, we're going to see that, yes, negative 11 equals negative 11. And we're good. So in other words, the answer must be negative 3. Very good. Now, boy, I have another one here that, ooh, this one looks bad. All right, we need a tricky one. Let's do that. You're not going to be happy when you see this one. Oh, wow. All right, let's see what you can do. Now, since you have fractions with different denominators, you might want to think about coming up with a common denominator and converting one of them to a different fraction. That's all I'm going to say. All right, I'm going to give you that helpful hint now. negative 5/3 is actually the same thing as negative 15/9. Okay, because if you just take it, multiply by 3/3, you'll get negative 15/9. Now, we can consolidate the constants onto one side here. Now I can subtract 9x from both sides. And I have negative 7x equals 19/9. So the last step is to divide both sides by negative 7. Now, x equals 19/9 over negative 7. Algebraically, this is the same thing as 19/9 times 1 over negative 7. And so that leaves me with x equals minus 19. Oh my God, what a messy answer. But that is correct. All right, if you got that one, I think none of them are going to be a challenge. All right, so now we're going to switch our gears a little bit into, oh, no, sorry, there's one more, then we can switch gears. Imagine the following situation. There's a math class, and the final grade equals the average of the 3 test scores. A student has already received grades of 80 and 90 on the first 2 exams and needs an average of 86 to get a B+. What is the minimum score he can receive on the 3rd exam to get that B+? This one's a little tricky because we're using an average now. So why don't we do this? Why don't we think of these 3 variables, T1, T2, and T3, to be the scores on the first 3 tests. We only know 2 of them. All right, we've been told that the first test was a 80, and then we had a 90. So we have 86 equals 80 plus 90 plus T3 over 3. So your job is to solve for T3. All right, so again, why don't you take a minute and see what you can come up with. All right, let's see how we do. Oh, somebody has it? 88. That sounds right. Let's find out. All right, so let's see what you would do. You can multiply both sides by 3. So that means 258 equals 80 plus 90 plus T3. And yes, it is 88. Nice job. All right, did everyone get that? All right, there's one more here, which I think you'll find to be quite easy by comparison. Multiplying a number x by 8 and then adding 3 results in a value of 27. What is the number? In other words, solve for x, but now your challenge is to set it up correctly. All right, so I want you to think about that for a minute. Oh, somebody's already got it. It was 3. That's exactly right. Well, let's see why. So the setup is that, remember, it says multiplying a number by 8 and then adding 3 gives us a value 27. Now it's just algebra. You just subtract the 3 from both sides and divide out that 8 and you're all set. All right, so we're almost done here. So the next topic, which I don't want to rush through it, is inequalities, which you recall means less than or equal to, greater than or equal to. We're going to do that next, but let's just say not today because it's already almost noon. So what we want to do is between now and then, now and Monday, I mean, you should look at the solutions to the chapter 5 problem set number 3, make sure you understand them all, and also start reading this chapter 6 set of slides so you'll see where we're going with this material next week. And so on Monday, we'll carry on with chapter 6. We'll probably finish the majority of it. And when that's done, we'll work on some problem sets, and then we will review for the midterm, and then I'll give you the midterm. But for right now, all you have to do is make sure you're keeping up with what we're doing. And if so, you're all set. And so I will just see you all next Monday. All right, see you then. All right, bye.
Thank
Bye.
you.
See you
Have a
then.
good weekend.
Okay, you
Thank you.
too.
Weekend, thank you.
All right, bye.